This video is about prime numbers. So if you have to ask what is a prime number, I'll spend a little bit of time on that, but here's the definition. A prime number is a natural number that's greater than 1 and has no positive divisors other than 1 and itself. So what's a natural number? A natural number is just the counting numbers, such as 1, 2, 3, 4, and so on. Greater than 1 is pretty self-explanatory, and then having no positive divisors other than 1 and itself makes more sense if we look at some examples. So here are some examples of primes. 5 is a prime because the only thing that can divide into 5 is 1, 2 doesn't go into it, 3 doesn't go into it, 4, but 5 does. So 1 and 5 are its only divisors that have no remainder. 6 is composite, and you say, what's a composite number? Well, a composite number is a natural number that's greater than 1 that's not prime. So any natural number that's not prime is composite. So 6 is a composite. Its divisors are 1, 2, 3, and 6, so more than just 1 and 6. 7 is prime because its divisors are simply 1 and 7. 8 is composite. It has divisors that are 1, 2, 4, and 8. So hopefully that gives you an idea what prime numbers are. An interesting question is, how do we determine if a number is prime? Is 11 prime? Well, you can pretty much figure out in your head that 11 is prime, but here's an algorithm for how to make sure. You start counting from 2 up to 10, and if that number that you've counted to is a divisor of 11, well, if it is, then 11's not prime. Because if any number from 2 to 10 is an even divisor of 11, then it can't be prime. If we get all the way to 10, then 11 is prime. So here's a simple Python function that carries out that algorithm. We define the function is prime. It takes in a variable called num. Then we do a loop. We say for I in the range from 2 to num, which takes us all the way to num minus 1. If num modulo I equals 0, that means if the number divided by I has no remainder, which means it's a divisor, then we return false, saying that that number is not prime. If we get all the way through the loop, then we return true, and the number is prime. So I wrote several tests to test this function. Here's one example. This is called test primes. We assert that the isPrime function, when passed at 2, will return true. Similarly for 3 and 5, because 2, 3, and 5 are all prime numbers. Here's a few more tests I wrote. We test some composite numbers to make sure that they're not prime. So we assert that isPrime, when it is handed 4, 6, and 9, it will return false. And we know that that's the case because 4, 6, and 9 are all composite numbers. Then we test negative numbers. We want to make sure that isPrime returns false anytime you pass it any negative number. We also test for 0, so isPrime returns false for 0. And we also test that isPrime returns false for 1. So those are a bunch of tests I wrote. Now let's fix this function because we can make this pass all these tests with 2 lines of additional code. Before it was failing those tests. Here we see that if we add this conditional, if the num variable we receive is less than 2, we simply return false and we're done, because any number less than 2 is not prime. That includes all the negative numbers 0 and 1. So that makes it pass all the tests. But this function is not very fast. Here's a large prime number. It's 46,324,987. That's a prime number. It's pretty large. If we use our current isPrime function on that number, it takes 5.2 seconds to figure out that that's a prime number. But we can do better. So let's quit wasting time. Given a number n, using our isPrime function, we can stop our loop at the square root of n, because any larger number than that would have to be multiplied by a divisor lower than that to result in n. To make that more clear, let's look at an example. If n is 16, we can stop the loop at 4, because even though 8 is a divisor that's greater than 4, we already would have found 2, and 2 multiplied by 8 is how we get to 16, so we would have already stopped the loop and we would have said that 16 is not prime. So here's the modified function that stops the loop at the square root of num. The only change is in this line. Instead of going all the way up to num, we go to the square root of num, and we cast that as an integer and then add 1 just in case. We may not even have to. And the rest of the logic is the same. This function can calculate the primality of our big number in under 1/10 of a second. So it's a huge improvement on calculating primes. But we can do even better. So here's a even larger number. This one has like 3, 6, 9, 12, 16 digits. It's a big number. It's not prime though. But it takes our most recent function, 5.2 seconds, to tell us that. That's unacceptable. So now we can see how to cut that time in about half. So let's only try the odd divisors, and here's why. If a number is not divisible by 2, then it's definitely not going to be divisible by any multiple of 2. That should be straightforward. So we only need to test the odd divisors. So here's the additional code that does exactly that. The first step we've added is we check that the number is divisible by 2. If it is, we just return false. So by doing that, we've now eliminated all even numbers from having to be tested. So we change our range to start at 3. We still go up to the square root plus 1. And now our incrementer is 2, so we're going 3, 5, 7, 9. Now that allows us to calculate that this is not prime in 2.6 seconds, which is half the time. So that's all for this video. In my next video I'll talk about generating primes and more things. Peace.